this video is on differentiating between relations and functions. It's lesson 25 in your book on pages 146 through 152. So we've got some definitions here. The domain of a relation is the set of all the possible values for the independent variable. Those are the ones you put into the function. Now, in an ordered pair, those are your x values. So your domain is simply all your x values. Now, that can be a finite set having a limited amount of elements in the set, or it can be an infinite set, like all the integers or all real numbers. The range is the set of all possible values for the dependent variable, or the outputs of the function. Now, in an ordered pair, those are the y values. Again, it can be a finite set having a limited number of elements, or it can be an infinite set, like you could say it was all the whole numbers or all real numbers again. A relation is just a set of ordered pairs where each number in the domain is matched to one or more numbers in the range. Basically, you can just say a relation is any set of ordered pairs. Here we have a relation, and we want to give the domain and the range of this relation. Now, remember, the domain is all the input values, or all the x values, and the range is all the y values. So when we write in the domain, we write it in set notation, which means we need those mustache things, and we just want to list all the x values. So we've got 2, then we've got another 2, we don't have to list that again, then we've got 8, we also have 5 as an x value, 4 is one of our x values, and finally 3 is one of our x values. So our domain is the set 2, 5, 8, 4, and 3, or you can put those in order 2, 3, 4, 5, and 8. The range is a list of all the possible y values. In this relation, or set of ordered pairs right here, we just list the y values. So we've got 6 as one of our y values, 10 as another. There we've got another 6, but we don't have to repeat it. We've got 1. There's another 6. Again, we don't have to repeat it. And also 9. So the range is 6, 10, 1, and 9. Or if you wanted to write them in order, 1, 6, 9, and 10. Here's another definition. A function is a special type of relation. It's a mathematical relationship, or relation, pairing each value in the domain with exactly one value in the range. Now that means that each x value corresponds to only one y value. For example, if you list the ordered pair 1, 2 in a relation, and then later you list the ordered pair 1, 4, this is the same x value, but it corresponds to different y values. So that would make your relation not a function. If each x value corresponds to only one y value, then you have a function. Now here we want to determine, this is an example that needs to be in your notes, we want to determine whether or not this relation, or set of ordered pairs, represents a function. So we're going to look at each of our x values. X value 3 goes with the y value 1, 3. X value 10 goes with 1, 0 goes with 3, 8 goes with 9, 4 goes with 4, and 10 goes with 2. Now, notice that we have an ordered pair 10, 1 right here, and then we have an ordered pair 10, 2 right here. So that means that when x is 10, y is 1, and when x is 10, y is 2. So we have two different y values for the same x value. So we say, no, this is not a function, because 10 corresponds with 1, and 10 corresponds with 2, or 10 has two different possible y values. Here's another example, and this needs to be in your notes. We want to determine whether y equals 1/2 x minus 1 represents a function. Now, remember that the way we tell if something is a function is if each x value has only one y value, or if each input produces only one output. Now, if we wanted to plug 2 in for x right here, we'd have 1/2 times 2, which is 1 minus 1 is 0. Now, if we plug 2 into x again, we will still get 0. We will get 0 every single time, and it's the same thing for any other real number. If we plug a number in here, we're only going to get one answer for y. Now, what that means is that we do have a function here. So yes, this is a function. And we can test it by plugging all these numbers into this relation and seeing that we get only one possible answer. If we plug -6 in, we've got 1/2 times -6, which is -3, minus 1, which is -4. If we plug 0 in, 0 times 1/2 is 0, minus 1 is -1. If we plug 2 in, again, we get 0. If we plug 5 in, we have 5/2 minus 1, which is 3/2. But we will only get that number every single time. So since anytime we plug in an x value into this function, we only get one possible y value, yes, this is a function. Now we can use the vertical line test to test a graph to see if it's the graph of a function. The vertical line test says that a graph on the coordinate plane represents a function if any vertical line intersects the graph in exactly one point. So what that means is that if I can draw a vertical line anywhere on this graph and pass through my curve more than once, then that is not a function. So see the sideways parabola here? There are all these lines that I can draw where I pass through this curve twice. That means that that is not a function. Now over here I have a line graph, and no matter where I draw a vertical line, and I realize these are not very pretty vertical lines, but no matter where I draw a vertical line, I will only pass through that graph once. So this one is a function. Here, we want to use the table to graph the ordered pairs and then determine if the ordered pairs represent a function. So it looks like we already have a graph here. -6, -4, if we were going to graph that, that's the one that would be -6, -4 right there. 0, -1, if we were to graph that, we would go to the left or right 0 and then down 1, so that's that point right there. 2, 0, we would go to the right 2 and up 0, so that's this point right here. 5 and 3/2, we would go to the right 5 and up 1 1/2, that's that point right there. And then 7 and 5/2 is this point right here. So this has been graphed. Now, we don't connect the dots because all the information we have says that these are the ordered pairs on the graph. Now, we have to determine whether these ordered pairs represent a function. So we're going to use the vertical line test. We're going to check and see, is there anywhere on this graph where we can draw a vertical line, yes, I know that's not pretty, but where we can draw a vertical line that will pass through any of those points more than once. Since there's nowhere on the graph that we can draw a vertical line that will pass through those points more than once, this is a function. So we can write, yes, it's a function. I spelled that wrong. There we go. That's an example, again, that needs to be in your notes. Now the dependent variable, y, is a function of the independent variable, x. So sometimes we write our equations in function notation. Now, this tells us about function notation. We just rewrite y as f of x. Now, in the expression f of x, what's in the parentheses tells us the variable. So whatever variable is in your equation, that's what goes in this parentheses right here. It can be anything. This thing outside the parentheses, in this case f, names the function. So this is the name of the function. So this means function f with variable x. And f of x means the same thing as y. Sometimes we write the dependent variable y as f of x. F is the name of the function. X is the variable in the function. This says write x plus 2y equals 5 in function form. This is an example. It needs to be in your notes. Alright, so we have an equation here. It's x plus 2y equals 5. Now, in order to write it in function form, the first thing we have to do is get y by itself. So we're going to use opposite operations to do that. And remember, we go in opposite of order of operations. So if I knew what y was and I knew what x was, the first thing I would do would be multiply by 2. 2 times y, get an answer. The next thing I would do would be to add x. So I'm going to do opposite operations in opposite order to get y by itself. So since my last thing was add x, I'm going to subtract x from both sides. Then I have 2y equals 5 minus x. I can't combine 5 minus x because one's a variable and one's not. Now the next thing in my list is multiply by 2, so I'm going to undo that by dividing by 2. So I've got y equals 5 minus x all divided by 2. Now that I have this, in order to write it in function form, all I have to do is replace the y with f of x. Now this is in function form. F can be different. It can be g, it can be h, it can be r, it can be whatever you want to name the function. But what is in here has to be x because that's the variable used in the function. Here's another example. This needs to be in your notes. Food labels list the grams of fats, carbohydrates, and proteins in a single serving. Proteins convert to 4 calories per gram. Write a rule in function notation to represent the number of calories from protein. Okay, so what we want is, we have our 2 variables here, calories and protein, and we want to decide which is the independent and which is the dependent variable. So we've got number of calories and grams of protein. Now, since protein converts to calories, we can say that the independent variable is the protein. That's what we start with, our input. And then the calories are our dependent variable, because how many calories we have depends on how many grams of protein we have. So it says proteins convert to 4 calories per gram. So if we want to figure out how many calories we have, we'll call it C, then we have to multiply the number of proteins by 4. Now if I'm going to rewrite that a little simpler, we've got C equals 4P. Now to write it in function notation, we replace our dependent variable, calories, with something like f of x. So I'm going to name this function capital C. I can name it whatever I want. And then I'm going to write the variable in my function in the parentheses. So P equals 4P. Calories as a function of protein, or calories with variable protein, equals 4 times P. And that's our equation in function notation. Now we have one last example. It says a student reads an average of 25 pages per day while reading a 544-page novel. Write a rule in function notation to find the number of pages she has left to read at the end of any given day. Now notice that this says how many she has left to read. So however many she's read is what we subtract from the total number of pages in the book. Now she's starting out with 544 pages. And we're going to subtract how many pages she reads per day. Now she reads 25 pages per day. So if she reads for one day, we subtract 25. If she reads for 2 days, we would subtract 50, because 25 for the first and 25 for the second. If she reads for 3 days, we'd subtract 75. So basically, we're multiplying how many pages a day she reads by how many days she has read. So we've got 544 equals 25D, and that's how many she has left to read, which I'm going to call Y. So how many pages she has left to read is how many pages she started with minus 25 times the number of days. If we're going to write this in function notation, I'm going to call it function f, and in my parentheses, I'm going to put the variable in my equation, equals 544 minus 25D. And that's my equation in function notation.